Welcome back, students. So in the last lecture we have seen that the stream function satisfies identically the continuity equation. So now we are going to proceed forward. So this was the place where we left off and we are going to start now. Okay. So what is the importance of a stream function? This helps us to disregard continuity equation, and therefore this means the stream function, and therefore the number of dependent variables is reduced by 1. Secondly, there is a disadvantage to it as well. The disadvantage is that remaining velocity derivatives are increased by 1 order, because as you see this is del square term. So therefore this is one of the disadvantages, but on the other hand the advantage is that the number of dependent variables is reduced by 1. Now what is the physical significance of stream function? So to look at it, if you see, psi can be written as del psi del x into dx plus del psi into del y to dy. All right, this is how del psi can be written, and you see del psi by del x we have defined minus rho v. Equation number 8, we use equation number 8, so it becomes minus rho v dx plus del psi by del y was rho u dy. All right, so this is nothing but this is rho v, velocity will remain v, we are writing as vector into the area vector. All right, and this whole is mass flow rate. So this implies actually that lines of constant phi are lines across which there is no mass flow, that is, they are streamlines of the flow. So you are noticing in this particular module the way of approaching the streamlines and the continuity equation has been very different. We have started from scratch and tried to show what we have learnt in our fluid mechanics class. Secondly, the difference between the values of phi of any two streamlines is numerically equal to mass flow between those streamlines. All right. So this are the two physical significance of stream function, that the lines of constant phi are lines across which there is no mass flow, and also the difference between the values of phi across any two streamline is numerically equal to the mass flow between those two streamlines. All right. So this concludes our continuity equation. Now we are going to the conservation of mass. So I think it's the right time to start the new page. All right. So we write conservation of mass. Okay. Newton's second law of motion states that F is equal to mass into acceleration. So let's divide. So I am again writing equation number 1 because we started a new topic. We call this conservation of mass. So this is equation number 1 in conservation of mass. So if we divide equation number 1 with volume. So volume we all in this module we are denoting by V. So this becomes F by V is equal to small f is rho dV dt, correct. So that is force per unit volume, or we can also write rho dV dt is equal to force small f, and that can be written as, there are two type of forces, one is body force plus one is surface force, and this equation we write as equation number 2. All right. So this F is applied force per unit volume on fluid particle. All right. So what is F body? We have to clarify that a little bit. So F body, so basically this is body force. So body forces are those that apply to the entire mass of the fluid element. Okay. Such forces are usually due to external fields. Such as gravity or an applied electromagnetic potential. Okay. So, currently magnetohydrodynamics effects. So, magnetohydrodynamics, hydrodynamics is dynamics, fluid dynamics for example, right, and which is caused by the magnetic force. So, these type of forces, magnetohydrodynamic effects, are ignored in current course, okay, current module basically, and we consider only the gravitational body forces, okay. So, F body is written as rho g, all right, and this we called as equation number 3, all right. Now, the other force is F surface force. So, first the definition: surface forces are those applied by external stresses on the sides of the element. This quantity, that is stress tau ij, is a tensor. So, surface forces are those that are applied by external stresses on the side of the element, and this is called tau ij. I will write it in a much all right, and this tau ij is a tensor. Okay. So, let us draw a figure. I am not very good at drawing, but I will try. All right. So, what we assume this dimension as x, all right, this has been assumed y, and this side it is z axis. All right. So, the stresses on the side needs to be represented, all right. So, this is x side, so the normal stress here is going to be tau xx, all right. So, the shear stress on this face, but going in y direction, is called tau xy, right. So, this particular face, and the one that is acting here is tau zx. So, if we similarly write on the y surface, all right. So, this is the y surface where this is the, all right. So, the upside is going to be tau yy, all right, this is going to be tau yx, and this side it's going to be tau yz. If we write on this surface, so on this surface it's going to be tau zy, because this is z surface, tau zz, and this is tau zx because it's in x direction. All right. So tau ij is the stress in the j direction on a face normal to I axis. Okay, so this has been our definition. Tau ij stress in the j direction on a face that is normal to I axis. All right. So we said that stress, this is a tensor, correct? So we need to write down, we actually have written down tau ij in that figure, but I'll write it down. Tau xx, you remember this similar type of tensor we had formed in this train in the last two lectures from now, 2 lectures before. Okay. So here tau ij is equal to tau ji. And what is this? What is the reason for symmetry? It is required to satisfy equilibrium of moments about the axis of the element. So the symmetry is required to satisfy the equilibrium of moments about the axis of the elements. So let us consider considering front faces of the element in figure above. Actually we wrote those stresses in the front, in the front faces itself. We try to write the total force in each direction due to stress. So d fx in x direction. So tau xx is in this direction and it's acting over the plane which is having an area of dy dz. I should actually show you once for this one. So if you see tau xx is acting in this direction, x direction, also tau yx is acting in x direction and tau zx is also acting in this direction, and multiplied by the corresponding. So, tau xx acts on area of dy dz, tau yx acts on area of dx dz, and tau zx is acting on the area of dx dy. All right. So, dfx is tau yx dx dz plus tau zx dx dy. So, similarly in y direction we write down the sum of the tau xy into dy dz plus tau yy dx dz plus tau zy dx dz. No, tau zy into dx dy. And similarly dfz is written as tau xz into dy dz plus tau yz dx dz plus tau zz into dx dy, and this all three equation we call as equation number 4. All right. So, for an element in equilibrium, these forces would be balanced by equal and opposite on the back sides, right. So, if the element is in equilibrium, the forces that we have written dfx, dfy, dfz, these forces should be balanced by equal and opposite forces on the back side. We have written the front faces, all right, back sides of the element, all right. Let us say, right, just assume if the element is accelerating, let us say it is accelerating, okay. So, that means the forces are not balanced. Accelerating, this is A, okay. Then front and back faces forces or stresses will be different by some amount, okay, some differential amounts, okay. So, suppose tau xx front, it is going to be tau xx back, this is what it means, tau xxx, sorry, not this, So tau xxx dx into del x into dx. We call this equation number 5. All right. Hence, net force on element in x direction will be dfx net, will be the differential, right? So that is going to be now del tau xxx dx into dx. This is the differential stress multiplied by dy dz. Same here, del tau y into multiplied by dy, all right, into dx dz plus del tau zx by del z into dz multiplied by dx dy. All right, sorry. And this is we call equation number 6. So we go to another page now. If we divide equation 6 by volume of the element, which is equal to dx dy dz, right, we get, so differential force by unit volume we called small fx, correct, is equal to, it will become del tau xx del x, so dx dy dz plus del tau xy dx dy dz divided by dx dy dz. So dx dy dz will get cancelled from up and below both. So fx can be written as simply del tau xx by del x plus del tau xy by del y plus del tau xz by del z, and this is equation number 7. All right. So equation 7 is equivalent to taking divergence of vector tau xx, tau xy and tau xz. That means the upper row of the stress tensor. Stress tensor is what? The tensor that we have written here. All right. So this is equivalent to taking the divergence of these divergence of vector. I have written velocity here. Stress tensor. Okay. So similarly, Fy and Fz are divergence of second and third row of tau ij. Okay, this simply means that total F surface force will be summation of these forces. So, in vector terms we can simply write tau ij divergence or del xj. All right. This is equation number 8, and it is a very nice point to finish our current lecture, and then in the next lecture we can proceed from this point and go ahead and finalize our the Navier-Stokes equation derivation and try to cover as much as we can in the next lecture. Thank you so much for listening.